Hi everybody and welcome to this video. There's Jeff Tepper, geologist, igneous petrologist, and we are near Granite Falls, Washington, west of the crest of the Cascades. I mean, come on, how are we supposed to do any geology? There's granite here, but is this the outcrop we're going to deal with? Not quite. We're going to go to an actual waterfall, South Fork of the Stillaguamish, next to Granite Falls. Get it? There's granite and falls. Let's learn from Jeff Tepper today. Thank you for joining us. Yes, this is part of the Idaho mini-series, but we're not going to Idaho today. But we're working on some themes we've been thinking about in the last few programs. Thanks, let's get started.
Part of the reason I think this is an interesting spot is that it's an intersection of two different stories. It's the breakoff story, but it's also the early Cascade story.
Okay. So the rough time frame of our igneous rocks today is roughly when?
Like 49 to 45.
Okay. Yep, we're right in the early days. So as we approach the river here, we're going to get louder and louder, I think. But we need the river to get some exposure to this unit. When was the last time you were in here? Were you mapping or just sampling some of the rocks?
No, so I was here about 10 years ago when the Washington Geological Survey was mapping this quadrangle. So we're in the Granite Falls quadrangle, and Joe Dragovich and his team were mapping the geology, and I came up to look at the igneous rocks mostly. So this is the Granite Falls stock.
Okay.
And it's an early Cascade arc Pluton, something like 44, 45 million years old.
Okay. Whose date is that? Is that yours?
That's a Mike Eddy
Oh,
date.
Mike Eddy.
It's plus or minus something like 68,000 years. Mind-boggling.
Okay. I don't know, can I follow you down here and just find a spot
Sure.
to look at some of this rock? And a stock that's a word we haven't used before.
So a Pluton is a generic name for any intrusive igneous body.
Yeah.
It doesn't have any real implications about size. If you say stock, that's a relatively small body, and that's as opposed to a batholith, which is a much larger body and by definition should be more than 100 square kilometers at exposure. So there's a small body here.
It wouldn't make you break a pencil if you watched this program and I called it a Pluton versus a stock. Would that really upset you?
I would be delighted.
Okay. Okay. Good. No pencils were harmed in the viewing of this program.
Those are synonyms. One of them just doesn't have any implications about size.
Good, good. Oh, nice. You got a face that you like?
I do, actually.
Okay.
I was attracted to that large rounded rock that has a dark inclusion in it.
Good.
Can we wander down there? Is that okay?
Let's do that. You know, before we do, let's just do a couple quick things.
Okay.
So as we take in this scene, we're kind of in the foothills of the Cascades, would you say?
I would say that, yes.
And how rare is this in Western Washington to see a big face of quote-unquote granite west of the crest of the Cascade down here in the foothills? Are there dozens of these things?
I don't think they're rare, but they're going to be restricted to river channels and places where there's been erosion.
Okay.
So, and not every river channel is a Pluton either, so.
Right. But this bedrock, and bedrock like it, is quite often buried under this dense carpet of trees in Western Washington.
Yeah, so except in places like this where there is river doing the erosion or road cuts where road construction has exposed things, there's a serious challenge in seeing through vegetation, Devil's Club, alder, all kinds of.
Okay, thank you. I'll follow you best I can without wiping out. beautiful.
All
Okay.
right, so there's a nice face.
Walk us through what you see here, please.
Okay, so one of the themes we might carry on through the day today is that there are several Plutons in this general area that are not greatly different in age, but have a very different story to tell.
Okay.
And so the Granite Falls stock here is an early Cascades Pluton, which means that it's related to subduction. And we would like to have a way of identifying this as being a subduction-related igneous body as opposed to some other sort of crustal melting story. And so what we can see in this outcrop are two things that tell us this is a subduction-related rock.
Okay.
So one is that there's a fairly abundant dark minerals in here, and they're black, and that's hornblende. And so hornblende, we've talked about before, is a mineral that has water in it, and therefore is particularly associated with subduction zones where there's more water than other tectonic settings.
Thank you.
And then the other feature here are these dark inclusions.
Yeah.
And those are also very typical of subduction-related igneous rocks.
They are.
Yep. And those are a magma injection story. So those are often called mafic enclaves. And the way they form is that you have a body of granitic magma,
Yeah.
and then injected into it is a pulse of basalt. And the basalt, being a much higher temperature, is more fluid, and so they don't mix together very well. There's a big viscosity contrast. So the mafic magma tends to break into blobs and never really homogenizes, and then it quenches and solidifies and remains in a discrete feature. So these are an indication of multiple inputs of basalt into some magma body that was sitting somewhere in the crust. We don't know exactly what depth this was, but they're very typical of subduction-related activity. For example, in the Idaho batholith, you would not find these because we don't think that the Idaho batholith was generated by input of mafic magma from below.
Yeah.
That was a crustal melting story related to crustal thickening and radiogenic heat produced by radioactive decay.
Well, that's wild. Without you being here, I would just assume these are true xenoliths, where you've got some cooled basaltic bedrock that this granite is coming up through. But you're not saying that. You're saying that the mafic stuff is liquid as well?
It was injected as a liquid.
Wow.
So we'll look around, but there's a variety of textures that you can often see that tell you this wasn't a cold chunk that was accidentally incorporated. This was a molten blob.
Here's a beauty. Let's
there's
go
a
look
rounded
at that.
one.
That's a beauty. Is the shape part of it? Like they're so round?
So they're rounded as opposed to angular. So
who's going to fall first? That's my question. I'll put my money on me. Oh, God.
all right, so often, and I can't make for sure in this case, but often crystals from the host can be found inside here. So they've been exchanging.
No kidding.
So I can't say for sure that these are that, but in some cases where there are distinctive crystals in the host, which is what we call the granite the host, you find them in here. Sometimes around the edge, and this isn't one of those times, but when a magma cools fast, it tends to be finer grained.
Okay.
And so sometimes the outer edge of the enclave, or the xenolith, is finer grained because this was hotter, this was cooler. When you mix the two together, this cools very fast and the edge becomes finer grained.
This is brand new to me. I've been in geology for 35 years. Have I been asleep, or is this some sort of new
No, but
way
I
to
think
view
once
these
you've
things.
seen these, you will never miss them again.
No kidding.
So they're everywhere. I mean, in this part of the world, because we have a lot of building stone, for example, that came out of quarries that are related to the Cascade magmatism. On the UW campus, I know there are in Red Square, there are enclaves in the steps at Suzzallo Library.
Mafic enclaves. I just thought enclave and xenolith were basically the same thing.
Xenolith to me is a broader term. It's
Okay.
just any foreign rock.
Okay.
Xenolith.
Right.
So that would include these,
Right.
but it would also include things that are, metamorphic wall rock fragments or anything that's accidentally incorporated.
Wow. These mafic enclaves are telling a subduction story.
Right. So they're sort of one of the characteristics of plutonic rocks in a subduction zone setting.
So if we're 44 million years old with this, we have the subduction going and has been going for a couple million years at this latitude.
I would say that this is a sign, this was a mature arc, meaning that there's not a great deal of chemical change that takes place between 44 million years ago and now. So this by 44 million years ago, we were producing magmas that are very typical of a subduction zone.
Okay,
But that was only maybe a million and a half years after the oldest rocks we see. So things became normal in a hurry.
So I like to push things too far.
Figuratively.
Am I going to see mafic enclaves in any vintage of plutons in the Cascades all through the 30s, all through the 20s?
Oh, yeah. Yep.
I go to a tattoo. I was up at the Tatoosh Pluton yesterday.
Oh yeah, they'll be there.
Really?
Yeah, because they're part of the process. So in a subduction setting, you're generating basalt in the mantle. It is coming up into the crust. Between the time it leaves the mantle and the time it erupts on the surface, often it evolves into something more like andesite. So there's often some kind of a reservoir beneath the surface where magma is sitting for a while, but it's being continuously replenished. And these enclaves are the signature of this replenishment process.
Oh boy, this is big. I didn't expect this so early. And maybe I should have bet on you.
So one place that these are exceptionally spectacular is in the Sierra Nevada, where the exposures are huge. And that was actually where the idea that these were injected as liquid was really first, I think, convincingly demonstrated, because you could follow a dike which was injected into a granite, and as you went along the dike, it turned into enclaves.
Oh yeah, it turned into enclaves.
Right, because at the beginning, at the edge of the Pluton, where it was already solidified, it was a dike, but when it got more toward the interior of the Pluton, which was still molten, then you had magma meets magma, and the dike just comes apart. So it was unequivocal, I think, in that case, that these rounded blobs that are everywhere started out as injections of basalt. Okay, so look, here's one kind of in 3D.
Oh wow. So devil's advocate, why can't that be? What are the reasons we can observe and say this cannot be a 60 million year old basalt that got swallowed up by this 44 million year old felsic magma?
If all you saw was one, it might be hard to make that argument. But we tend to see a whole spectrum of textures, from sort of diffuse, largely assimilated, where it's just a shadow,
Okay.
all the way to things that, like a dike. So that and so turning something into this diffuse, sort of wispy relic
Right.
is easy to do if they're both hot
Yes.
and one's partially molten. It's pretty hard to do that if it was a cold rock to begin with, and this is a shallow Pluton. There's not a lot of heat and time for digesting things. And then you'll see textures that just look like, drawn out like taffy. like it's just been drawn out and folded. So it looks mechanically like it was soft and ductile, not like it was brittle and cold.
Are all of the enclaves mafic? Is that important?
They don't have to be. So some of them hybridize. They interact with the host, in which case then they can become more like an andesite. And I think that depends on how long between the time the basalt was injected and how long before the Pluton solidified.
Huh. Okay, so far we have subduction generated magma because of hornblends and because of mafic enclaves.
Right. And so this being one of the older Plutons that has the traits of a subduction zone is part of our evidence for when the Cascade Arc turned on.
Thank you. So Tatoosh Pluton, supposedly
there'll be enclaves.
Spirit Lake Pluton.
Spirit Lake will have enclaves. I would be willing to bet.
Snoqualmie Batholith.
Tons of them. Yep. They're everywhere. Once you see them, you can't miss them. It's kind of cool over here if you want to at some point work our way over here.
Got something?
So this is a huge one. You can see the contact going
really?
there, and then it's over here, and it wraps around. And then on this side, there are enclaves inside of enclaves. So there's multiple generations of.
This is a light color? No, I'm getting confused.
So this is the host.
Okay.
And most of this face.
Oh.
This one almost looks like a dike.
Oh, I see.
So if you come around on this side, it's a better.
Oh, wow.
But this is what I wanted to point out. There's an enclave in this other. So there's more than one generation
I see. Oh, yeah. Okay. So the mafic enclaves are quite often these little rounded dollops. But quite often the dollops are associated with something bigger, like a planar dike.
The dollop is a disaggregated something bigger. Look at this here. It comes down like this, and then it goes in like that, and comes around. So that's a very, I don't know if you can see that well.
See it, you bet.
That's a very mushy looking feature. And you could imagine this is going to break off, and it's going to become one of these.
So when Mike Eddy came here to get a date for the Granite Falls Pluton, he was staying away from the mafic stuff?
Well, he would stay away from the mafic stuff because that's not likely to have zircon in it. So this, zircon is more commonly found in rocks that have more silica, so like granites, not in basalts. And then this is a very fine-grained rock. So it would just be more challenging if you had zircons to find them because they'd be very small.
But if he's got his precise date on this, the date of this stuff has to be like the next Tuesday or something.
Yeah, the same.
The same, exactly.
The same. I mean,
they're liquid.
Even with Mike's 68,000-year uncertainty, these are the same.
Okay.
You know.
Okay. So have you worked on these enclaves, written a paper, or is there somebody else who did some work on this?
No, I wrote a paper on enclaves in the batholith that I studied for my PhD.
The Chilliwack?
The Chilliwack. And I guess I had sort of this epiphany moment when I was walking up there with my advisor, Stu McCallum, and he pointed these things out, and I hadn't really paid attention to them. And then, just like you're going to be, I thought once you see them, you can't stop seeing them. So people have looked at these for decades, and they've had different interpretations. The early interpretation was that, you know, when you make a granite, you're melting something in the crust at depth, but you're leaving something behind as well. There's a residue of melting, and these were interpreted as the residue of melting that just came up along with the melt.
Yep. And
that was in part because if you analyze the enclave and the host, they have similarities. So they'd be, you know, you could match this enclave and its host in a different batholith. You'd have a similar matching, but they'd be different between the batholiths. So this chemical similarity was interpreted as evidence that the enclave was genetically related to the host. And then, you know, to me, the real breakthrough came, I think it was in the early 90s when a guy named John Reed, who was teaching at Hampshire College, took his students to Yosemite, and they saw these magnificent outcrops in the Sierra Nevada batholith, in which you could see in a big face a dike, which started out as a dike and then kind of got squishy, and then you just kept walking, and then the next thing you knew it was enclaves. And so that, you know, visual evidence was so compelling. And then they did chemical analyses and showed, yes, the enclave is the same as the dike, except maybe it has begun to interact with the granite. So the dike might be more like the original basalt, and the enclave is a little bit like the host. So that explained why there was this similarity between enclave and host, because they're interacting while they're sort of in this mushy state. So I think most people now would agree that these are the result of injecting basalt into a pre-existing magma body. And that can happen over and over again in an arc setting. So there can be many generations of enclaves, just like the one we saw here a second ago.
And viewers, I will put this PDF of the map and the pamphlet at nickzentner.com. Click on the word Cascades in the upper right hand corner. You'll get to this thing free, and you can download this if you like. Joe Dragovich, Skylar, Megan, blah, blah, blah. Jamie, there's Jeff Tepper.
Yeah, so look how many team members there are.
Yeah.
They all have different areas of expertise.
Andy Dufresne.
He's the dating. He does the uranium lead dating.
Wasn't he in Shawshank Redemption? Isn't he the guy that broke out of prison?
I don't think that's the same Andy.
Okay, right.
Oh, you're right, there was an Andy
They
there.
had a rock pick too.
Okay.
All right. Well, I got to follow up on that. Tim Robbins is part of this project. Okay, I'm sorry.
Okay, so EIGD is this pink unit, which is sort of several close-spaced but separated outcrops. There's the river going through it.
Yes.
So we were sitting down here somewhere just a few minutes ago.
Got it. These are Chalice magmas.
These are Chalice time period, but this is the sort of tail end of Chalice, but we're way too far west. So these are Cascade Arc beginning.
Oh yeah, oh yeah.
So this is one of the things that's challenging in piecing the story together, is that 3 events overlap in time. The end of the slab rollback, which is mostly in eastern Washington, and probably, as far as I No, not any farther west than Wenatchee.
That's already happened. Your breakoff belt has already happened.
Right, but the breakoff belt is about 49, 50 to 48 or something like that. Those rocks are just east of here, 25 minutes or something. So we have this intersection between rocks in a linear belt that are related to breakoff.
Yep.
Farther east from there, we have the rollback story, which is migrating this way.
Yes.
And is culminating around 44, 45.
Including these guys?
No. That's happening farther east.
Okay.
And then here's the arc turning on. And so these rocks look very different than the breakoff belt rocks. And that's if we at some point go over to Mount Pilchuck, those are breakoff rocks. And I'm hopeful that if we looked at them, we'd say, well, these don't look like arc rocks. Although their age is only about 4 million years older.
Do the Mafic enclaves work in lavas as well?
Yes. Yes. And it's somewhat less ambiguous there because those things are quenched. So there's much less time for things to re-equilibrate and hybridize.
So in a weird way, this position of the triple junction thing is even a factor here when you're trying to decide which plate is subducting, why wasn't it subducting earlier. All of that is all I'm still kind of thinking all roads are leading to trying to get some kind of consensus, if possible, between the tomographers and the surface geology people, the geochemists like yourself.
I think we're pretty close. I think we're, in terms of Washington,
yeah,
I think we're pretty close. I think things are certainly more ambiguous or complicated in Idaho and points east.
Right.
But here, I think things are falling into place reasonably well. For your desk.
Hey.
You'll never be without an enclave.
Thank you. I know right where it's going, next to the gumball machine.